A warm welcome to another session, Data with Nick the Greek. Um, Last time we learned about how partitions influence saving Parquet files, and today we're gonna turn it around. We're really gonna have a look how the data loading with Parquet works on Spark, especially looking on the number of partitions and distribution of the data. And for me, it's really interesting because I deep dive into a topic quite a lot the past few days and learned some new things even by myself. And thought I can make one session to just explain it, but it's actually highly complex and there are a lot of influences. So Spark actually generates the number of partitions when we're loading the data. So there are gonna be multiple small videos on it. And today we really start with the basics. And you might ask, okay, why do we really want to deep dive into the complexity of Spark, how partitions are generated during loading? And I mean, the main thing is, first of all, it's important to understand how Spark creates partitioning to really influence it. And you already saw in the previous videos that the number of partitions, empty partitions, the distribution of data can even in error transformations already influence a few things. And if you can avoid those expensive operations, for instance, repartitioning, but also coalesce has some smaller overhead. Already just by defining with some simple parameters the way data is loaded initially from the file system to the partitions, you just make your whole process way easier and also more performant. So you basically solve the issue already in the beginning, not halfway. And that's where we're gonna start the deep dive today, and going step by step over the next videos a little bit deeper. So as a setup for today, we have here a new added package. So I just added the link. You can have a look on by yourself. I found this really easy to use Spark package where you can analyze your data and data distribution in your file system quite easily. And then we don't need to jump too often into the Spark UI to see how the data size and row records have been divided. Basically, this tool is doing it for you. And as we're also gonna look a little bit deeper into Parquet the next videos, it's already helpful to just introduce it today. So we have today a few functions which we're gonna use, like a data write generator. So basically I just created a function which, based on the number of rows defined and number of files, which is equivalent to the number of partitions when saving, it generates me quite uniform distributed files. So meaning 1,000 rows and the number of files of 4 would generate me a Parquet file with 4 snappy Parquet files in the background. Not deep diving into this right now. It's basically serializing compressed file in the background, and it would generate me 4 files with, if we set 2,000 number of rows, it would be 500 number of rows per file. Then we're gonna use some configuration today. We're gonna learn about this in a bit. I just generated a function which sets those 4 configurations for me, and well, the function has the default values, but about that in a little bit. And the last thing for further analysis, I introduced the Parquet module, which introduces a Parquet partitions function. And basically here I did some calculation. You're gonna see the table in a bit, just giving you some information about per partition, how many bytes, how many files, and how many rows you have within your data. And with that, let's start talking about what actually influenced the partitions. And I also added some references if you want to deep dive into it afterwards. So the first thing is doing the creation of data frames before doing the partitioning is the number of cores is influences the number of partitions also during loading of the data. And I mean, it makes sense. You don't want to keep your available cores unused. And correctly speaking, it's actually one of the configurations we saw above is the Spark SQL file's min partition number. So you guess it, it defines the number of minimum partitions to be created. And this is default equal to the default parallelism. And as you know, the default parallelism is defaulting to the number of cores you have available. Then the file size, or better estimated file size, influences the number of partitions. We're gonna see it later. Also the number of Parquet files, and also I learned, and so you're gonna see it also very soon, is Parquet files are split in so-called blocks, row groups, and even usually a snappy Parquet file is not separated. If the Parquet files become bigger, they are separate, but based on a completely other logic, which might also influence our performance or empty partitions later. Then the parameter we're gonna focus today, the max partition size, which basically limits the size of a partition, and it defaults to 128 megabytes. And then a parameter which, is a little bit more complicated to explain, but it's called max cost per bytes, and basically represents the cost of creating a new partition. That's especially relevant if you have smaller files. It defaults to 4 megabytes, and usually you don't really need to adjust it because it doesn't bring a huge performance benefit. But technically what it's doing, once we're gonna deep dive a little bit into the algorithm, is it does a so-called padding. It adds those 4 megabytes, for instance, in this case, to the file size. And if you have a lot of smaller files, basically it tries to create 4 megabyte partitions instead of generating a bigger number of partitions, which is, it brings more benefit to have like all the small files into one bigger partition than and even having them, the other cores, empty running, than having those small files distributed across the cores. That's what it roughly does, but that's why we're gonna deep dive also in a later video to have a look on max cost per bytes. But already mentioned below, this parameter, and I'm not even sure if, or at least I haven't understood why it's even properly integrated that way into the algorithm, but usually doesn't bring a really significant performance benefit. So, as already mentioned, why are we doing it? And I also added here as a recap how partitioning is influencing our performance. So what we want to look today is number of partitions, but we should be aware that we're doing it to have a good parallelism and a good distribution of our data. And with that, let's have a look into a basic algorithm, how Spark is basically splitting the data. So we learned that we have the max partition bytes, and this is basically limiting the number of data per partition. But additionally, we have the number of partitions. And basically what we're doing is, so let's say we have a 100 megabyte Parquet file with, of course, multiple number of files in the background. But what the algorithm is basically doing is it divides the whole file size, the 100 megabytes, through the number of cores we have. And I mean, this makes sense because Spark is smart enough and wants to be smart enough to split the data across the partitions to process them more efficiently. And that's why we calculate a 24.5 megabytes size per core. And then we're just looking on the minimum, meaning, so now our max partition bytes in default is 128 megabytes. So the limitation per partition is 128 megabytes, but the size we have per core is only 25. meaning the minimum would mean this is gonna be the partition size. It doesn't make it doesn't make sense to take the bigger value, because otherwise you would move all the data into one core, and the other core is gonna be empty. So that's where the smartness of Spark is there. And then the number of partitions, roughly said, is just the file size divided by the partition size. So let's play around a little bit with it. So let's take a file size of 64, and our max partition is going to be 128. So as we expected, file size for 64, size per core is 16, partition size is 16, and our estimated partitions are 4. So let's go with the file size a little bit bigger, let's say 100 megabytes. Same logic, nothing happened. Then let's go to 200 megabytes file size. Same logic, because nothing happened, because the size per core is still 50 megabytes. So now to not increase the file size even more, let's go with max partitions 45 megabytes. Now you saw what's happening is the max partition size is 45. It says, okay, we're gonna have 5 estimated partitions, but attention, we gotta see it a little bit in the experiments. The smaller Parquet files, the snappy Parquet files, are actually not splittable. So let's imagine we have here also 4 files. And then this would be not possible. If we have, let's say, 20, 30 files in the background, then it's possible. So that's where the influence also of the number of files happening. It depends on the use case if this is actually possible, and that's what we're gonna see in a bit. So we can, if we go with max partition even to 200,000 megabytes, it just doesn't make influence. It just defaults to the number to the number of partitions. So basically, it's like a safety mechanism to say, okay, if you wrongly or too low set your max partitions bytes, it just defaults to the number of cores and creates your partitions based on that, to not create too small partitions, or not use your whole your whole capacity which you have in your executor. All right, so now let's really take a look into one experiment. So we're gonna start with 3 Parquet files. So the first experiment gonna be 4 files, 64.8 megabytes per file and 259 3 megabytes. And here we're gonna run a few functions. You're gonna see in a bit what it does, and here we can set our configs. So it's 128 megabytes, the default which we're gonna start. And here we can see a few things. So first of all, we can see the file size, the average file size of 64.8 megabytes. We can also see the size per kernel algorithm is 64.8 megabytes. We have 4 estimated partitions, and we can now see the actual number of partitions. It's 4. So our algorithm worked quite well. Let's also have at least once a look into the Spark UI for that. So here we have the loop, right? We see, okay, there's a slight deviation, but we can see that we have 800,000 rows, the same as our data set, and the same as this table is showing here. Yeah, we have here well distributed data set also regarding the execution. So that's actually a good outcome which we have here. Now let's repeat the experiment and go up. The same result as we evaluated before in our theoretically algorithm. We have again, that takes a little bit. So we have again 4 partitions and also 4 partitions with each one number of files and the equivalent size here. Now let's make it a little bit more interesting. Let's go down to 60 megabytes as the average number of files is 60, as the size per core is also 60. So now the interesting part. So as before, we saw our estimated number of partitions. So ignore this more complex algorithm, we talk about it next time. But here the estimated number of partitions is 5. So we always have to round up, of course, so it's actually 4.3. I forgot to mention this before. And then you see we generate 5 partitions, but now Spark didn't distribute the data size across the, what do we have, 259 megabytes across the partitions. But basically it says, okay, I cannot split those snappy Parquet files. I have to keep them at once. And what we're ending up here is, with a with an empty partition. And let's also confirm this into the Spark UI in this case. So we are having here our 5 tasks. You see it. And I mean, it messes up a little bit. In this case, we don't really have like a big performance benefit, but imagine you have like suddenly 1,000 of those small tasks. Let's also have a look into this, right? 4 seconds. And this one, no, 4 seconds. So it's pretty much the same thing. So now let's play around a little bit, and I don't know, let's go with 10 as max partition. So our basic algorithm estimates 26, but we have 28, and the reason for that is, at least that's my assumption, is that we have some kind of padding, what I mentioned before already here. So here just divides through the number of files, but what I explained before is, let's do the calculation if this actually works. So we see that we have 28 number of partitions, and let's go first and confirm this into the Spark UI. So we have the right, surprisingly still at 4 seconds. So for the small data amount of data, we didn't realize it. But I mean, what you can see here is we have a lot of small partitions, and actually only 4 of them contain data. So that's basically how you can mess up your your scheduler and your Spark jobs. And that's something also we want to avoid for the following jobs, because if you do a join and so on and have so many empty partitions, it can even mess up things there, or even narrow transformation. Doing a join properly, the shuffling gonna resolve it afterwards, because it's resorting the data and realizes there's not really any data in there, but it's still gonna mess up things a little bit potentially. So let's come back to the calculation. So we said we have 64 megabytes of data per file. But basically I said before that it does actually a padding of 68.8 megabytes. So, and now what we are, this is gonna be a little bit complicated, but basically what we're saying is, or actually let's calculate it with a little bit of bigger max partitions than we have less to calculate. So let's go with 50. The concept is still the same. Here we are still with the correct number, but let's just understand what actually happens in the background. So we have 68.8 megabytes actually, because we have 64.8 megabytes per file, plus the 4 megabytes which we're getting from the padding. So, and now we say we restrict the partition size to 50 megabytes. That means basically we have to distribute for each file 18.8 megabytes. So this is 18.8 megabytes. So now what Spark is checking, we need at least one more partition. So let's go with the fifth partition divided by 18.8. Okay, we can fit there only 2 files. Okay, 2 files is correct. If we wouldn't have gone with the padding, we would have had here 10.8, and then there would be no, nonsense. We would have gone with 40.8. So there we would have fit 3 files. So basically here the 3 imaginary files which don't really exist are calculated correctly. So, and then the other 2 are going into the next partition. And that's basically the reason why there's some deviation, because actually you would have to consider the padding, and you have to consider that that's always 2 files, even let's call those imaginary files or imaginary splitted out data is basically estimated in there. Okay, let's now go with an experiment where we have a little bit more data. So in this case, we have a size of 518.9 megabytes, but the same average file size. So let's start with 128 megabytes. So our algorithm says that we have 5 partitions. We have here a little bit more. So why is this the case? So we said again, Parquet files are not splittable. And if you're looking into 128 megabytes, how many of those files can you put in there? Let's divide 188 by 4.9, and we're gonna realize it's 1.9. So basically the second file you cannot fit into there. So it makes totally sense that it tells us that it's 8 partitions, and luckily this is even a very good partition size. So now let's say that's roughly 65, so 130. Now let's see what happens with 130. So basic algorithm at least says we're gonna have 4 actual number of partitions, and you're asking yourself, why the hell do we have this? So that's where the padding is coming into place again. So basically, we have to calculate with 68.9. So, and 68.9 times 4 is 275. Okay, now actually we have to times 2 because we want 2 files into one partition. That's why I stuck this well for a second. So it's basically 138. This happens when you do calculations on the spot sometimes. So we have min partitions, and voila, we have the actual number of partitions reduced to 4. And I mean, that's important to understand that it's not only about looking at the file size, but this padding really influences the number of partitions happening in the backgrounds. So let's, especially now when you're having multiple files, if the number of files is equivalent to the partition, usually it's clear how the data are going to be partitioned. So now let's do the experiment again to go a little bit lower than the average file size. Or let's start already to see if something happens if we go below the padding size. So 68. Our algorithm says we have 8, and also indeed here below the padding size no new partitions are created. Let me go, here we are, let me go back here. So and now let's go below the average file size, 64. Here you see our first partition being added, again with empty files. And yeah, that's pretty much it here. One thing which I'm curious by myself right now is, so we have here also size per core. Let's see what's happening here, slightly above and below. So 130. It still creates the actual number of partitions, yes, due to the padding, which we set, and 128 we already gave a try. Okay, let's make this the same experiment with another file. So we start with the 128 megabytes. This time we have also 8 files, but they're a little bit smaller. And here our default, so the logic is pretty much the same. Here we're estimating 5, but again we have the issue. Let's see why we have 8 partitions here. So if okay, I just have to copy one thing over. That's something I misconfigured. So path, actually we have the same experiment as before because I have to copy the path over. So now one more try. So let's start with 128 megabytes. And now it makes sense that we have 4 number of partitions. So of course, why 51.5? So let's say 52 is 104, and that means 2 files are fitting in here. So if we go 48 times 2, again the same thing is 96. You're gonna see that we didn't estimate the padding, and it generates 8 partitions. But if you're gonna go with 52 times 2, 104, including the 5 megabytes of the padding, it's gonna be worthy. It's gonna come out as an actual number of partitions for. And with that, I want to thank you today for this session. You already saw there's some complexity at the beginning, and but you really can see, okay, max partitions bytes really influences the number of partitions. If you set it wrongly, it can create empty partitions which you don't want. If you set it correctly, we can see that we have a well-distributed data set, and we can experiment a little bit with big amounts of data and bigger number amounts of files to really see, okay, how we can then set also partition, well, a max partition bytes where you have like really a uniform number of partitions and also size later on. And as always, feel free to comment, feel free to challenge if things have been slightly different or even wrongly. Communicate, always learn also from the community. And of course, please follow my channel if you like this video and want to see more of those kind of deep dive technical videos into Spark and other data concepts. Goodbye.